Okay, and we're good. Let me share my screen. So this actually, out of all the sessions we've had so far, this one has like the most material. So I'm gonna go fast through some sections I think are somewhat easy to grasp. I'm gonna spend a little bit more time on some areas that are technically challenging, I'll say. And then you just let me know, if I speed through something and you need some more explanation, just let me know, and we'll go through it. Okay.
Awesome.
All right. Can you see my screen? Does that look good?
Yes.
All right. So we're going to go through just general concepts with regard to aerodynamics. I'll talk about major parts of the aircraft, 4 forces of flight. And after we talk aerodynamics a little bit, we'll do some basic flight concepts like turns, climbs, descents, stuff like that. We'll talk about load factor and stalls. And then when we did this live several weeks ago, we got up to 2 hours before I got a chance to talk about stability. So I've got a placeholder there to do a time check, and if we're good, we'll talk it. If not, we'll try to cover it in a future class. Okay.
Okay.
All right. So general aviation aircraft may be obvious, but these are the widely known popular parts of the airplane: the power plant, the propeller, your wing, landing gear, which can be fixed or retractable, the fuselage, and the empennage. And sometimes fuselage and cabin are used synonymously. But these are the highest level, most major components you can get on your typical general aviation aircraft. For our discussion on aerodynamics and basic flight concepts, it's important to have at least a grasp on Newton's 3 laws of motion. Now, are you familiar with some like simple high level physics stuff? Have you studied Newton's 3 laws at all?
No, I specifically studied music, so I would not have studied physics.
Oh, okay, there you go. Completely opposite sides of the spectrum. Okay. Well, I'm going to go through them here. They do make intuitive sense. It's not very difficult stuff, but there's 3 separate laws, Newton's laws of motion. The first law says that an object remains at rest unless acted on by a force, or remains in motion unless acted on by a force. So this is very simply your car is driving down the street and it doesn't stop until you hit the brakes, or your car is sitting at a red light and it doesn't go until the engine pushes it. In physics, it's used to basically say that if an object's moving, it's going to continue to move until something puts a force on it to do something different, whether that's stop or change directions or what have you. In the flying world, it's typically used to explain that if you're flying straight and level in cruise, and one of your flight controls, like an aileron or a rudder or something, deflects air, that'll cause the aircraft to change its direction or move in a different direction. The second law states that that the force, so the force that was described in the first law, is equal to mass times acceleration. Out of the 3 laws, even though these are somewhat simple, this one tends to be a little bit more theoretical, tough to explain simply. But basically, if you've got a coffee mug on a table, and you push that coffee mug across the table, the force that you impart on the coffee mug is directly related to that mug's mass, and that's intuitive, right? If it has a higher mass, you've got to push harder. If it's got a lower mass, you don't have to push as hard. So the heavier something weighs, the more force you have to impart on it for it to actually do something. And then the third law, which is outside of the physics world, is known by a lot of people, is when one body exerts a force on a second body, that body simultaneously exerts a force equal in magnitude and opposite direction in the first body. And the easiest way to explain this one is when you stand on the floor, the weight of your body is exerting a force on the floor, and the floor is exerting an equal and opposite force onto your feet. Same in the airplane world. When we're describing lift, if the aircraft is in straight and level flight, the wings are imparting a force that's equal and opposite to the weight of the aircraft, which causes it to stay in the air. So these three forces, as we go through the charts, you'll kind of be able to point to different ways that these laws of motion are used in the aerodynamics discussion.
Okay.
And once we kind of understand the major parts of an aircraft and Newton's three laws, we can start to have a discussion of the different forces that act on the aircraft. You may have seen a diagram like this before, but the four fundamental forces of flight are thrust, lift, drag, and weight, or gravity. Thrust opposes drag opposes thrust, and lift and weight oppose each other directly. Now we'll learn in a little bit that these different forces can oppose each other. They can, like, thrust can oppose drag. It can also oppose weight in certain scenarios, but these are the most fundamental forces that you can take to the aircraft. When we start describing aircraft performance planning, like we're going to do on Thursday, these elements will come out in that planning. You'll see different elements of thrust, of lift. We already had the session on weight and balance, where we learned more about how we do flight planning for weight and balance. So these forces come out all the time when you're flying and when you're flight planning: thrust, lift, drag, and weight. Just curious, was this a concept you were kind of already familiar with?
No, but I was able to read it in the pilot's handbook. So.
Oh, okay. Mm-hmm.
I mean, clearly gravity and lift, but the thrust of the drag, no.
Yeah, gravity and lift, those are sometimes obvious. Thrust is, a function of the power plant, whatever engines are driving your airplane. And drag's actually really, you think you'd understand drag until you start to learn about it. And drag actually has some concepts that are a little bit difficult to grasp, but we'll get into that. The four forces simply act in their relative directions. Thrust typically acts forward, drag backwards, weight always acts towards the center of Earth, lift opposite weight. But the forces can also be broken out into what are called components. And I've got just one example of many here on the screen. But thrust is providing the power for the aircraft to fly through the air. Drag is opposing that force. And in this scenario where the aircraft is climbing or has a positive angle of attack, down here you've got a force component. It's the rearward component of weight. If you look at this red arrow here, that's the weight of the aircraft acting directly down towards Earth. You can break that force out into two components: a perpendicular component, which is this green dotted arrow right here, and this black arrow right here, which is labeled the rearward component of weight. So each force, if the aircraft is not flying straight and level, can be broken out into these components. The rearward component of weight acts with drag, so it opposes thrust. And this conceptually makes sense, because if you're trying to climb, if you pull back and climb the aircraft, the airplane's only going to be able to climb so high until it stops, runs out of thrust. Right? The engine only has so much power to provide thrust. It'll only go so high until it runs out of juice. And that is the force of that rearward component of the weight actually working against the thrust. It's helping the drag vector. Do those components make sense?
Yes.
Okay. There's countless examples. I mean, if you take this example and do the opposite, if the airplane is in a nosedive, then you've got the call it the forward component of weight, because this would be in the opposite direction. The forward component of weight would be acting with the thrust, so it would be adding force to the thrust, and the airplane would pick up speed. Would go a lot faster than it would typically go with just the engine providing the thrust. All right, I'm gonna jump into the separate forces. We're gonna spend some time talking about each one. A couple of the forces are easier to understand than others. Lift and drag are by far the most complex. Weight and thrust are a lot simpler. So we're going to spend a lot of time talking lift and drag. So just stop me where I'm at if I gloss over something or something doesn't make immediate sense.
Okay.
So this is just clear some definitions here. When you look at an aircraft wing, at an airfoil, you've got an upper surface, a lower surface. You've got a leading edge and a trailing edge. And you've got these two geometric lines called a chord and a camber. And from a definition perspective, these will really be the only wing definitions you'll need to know. However, the chord line and the camber line have they are utilized in other areas of flying, I'll say aircraft systems and stuff like that. So the chord line is a straight line drawn from the leading edge to the trailing edge, and it is parallel to the aircraft. So you basically draw a line straight from the leading edge back to the trailing edge. The camber line is also a line that connects the leading edge to the trailing edge. However, you draw the line such that all points between the upper and lower surface are equidistant. If you notice on the chord line that cuts straight through here, there's a lot more distance between the upper surface and the lower surface. That the camber line is equidistant. You can see it curves, making up for the distance issue between the upper and lower surface.
Got it.
Yep. And this is important because I'll say the more disparity there is between the camber line and the chord line, meaning I guess the fatter the wing is, the more lift it will generate. So if you have a more aggressive camber line, meaning your upper surface is more curved and further away from the midpoint of your wing's going to be generating a lot more lift than a flat wing. Now, the downside to that, of course, is it's also going to create a lot more drag because it's bigger. So there is a sweet spot when it comes to wing design. But from a cross-sectional standpoint, these are the major definitions of the airfoil: leading edge, trailing edge, chord line, camber line. Sometimes you hear it called mean camber line, average camber line, but those are the major wing definitions. Now, how does the wing work? Now, before I jump into this is where things geek out a little bit. Have you studied any? I'll call it aerodynamics, where they've explained airfoils and how wings work. Are you walking into this with any preparation?
No.
Okay, I'm gonna explain it how it was explained to me, and I think it makes a lot of sense. Bernoullis Principle, which governs why an airfoil generates lift, is an extremely complex physics phenomenon. And I have heard so many people explain it differently. Probably the most popular way to explain this principle is you fill up a balloon, you hold it with your finger, and then you let your finger go. And what does the balloon do? It flies away, right?
Uh-huh.
Well, that is in essence Bernoulli's principle. However, ask that same person exactly why the balloon flies away and what the air pressures are doing and all that, and it's very difficult to explain. So I'm going to explain it this way, and you can tell me if it makes sense or not. I'm going to start with this pipe, and the pipe is a straight pipe. It doesn't have any elevation changes, and it's got a fluid in it that is constant, meaning it's, if it's water the whole way through. There's no leaks in the pipe. It's sealed, so there's no fluid loss or anything like that. This pipe goes from a diameter of, let's call it 5 inches, which is the size of the pipe here to the left where my arrow is, and it squeezes down to a smaller diameter. We'll call it, just for sake of argument, it's 1 inch in diameter. And then it opens back up to the same diameter that the entry point was, so 5 inches. Well, Bernoullis Principle states that the fluid, when it reaches that constriction, will speed up. And it also states that the pressure will decrease. The fluid pressure will decrease. Now, if from a common sense standpoint, this makes no sense at all, right? You would think, hey, if the pipe has a smaller diameter and it's constricted, you think that the pressure would increase, right?
Mm-hmm.
Yeah. Well, not the case. Actually, there is a higher velocity in that section, and there's a lower pressure. Now, the higher velocity, if you ask me, the higher velocity makes sense. You're trying to squeeze the same volume of fluid through a smaller space. But the pressure thing, I until someone explained it to me, the math behind it, I really could never understand that. So for now, just know that as a fluid goes through a constricted pipe, it speeds up and its pressure drops. And as it leaves that constriction and goes back into its original diameter, it slows down and its pressure increases back to the original value. And I'm gonna go through the physics behind that here. Okay, so this is very simply, this is Bernoulli's equation. And I've got this equals constant here for the purpose, or for the reasons I mentioned earlier. There is no fluid loss. There's no leak in the pipe, and the fluid does not change. It does not change density. It doesn't change any of that. It's either water or air, or it's a constant fluid. And so the math behind this principle is three different parts, and I'm gonna talk about them, and I'm gonna explain them in full. So if you already understand some of this, just go ahead and stop me. There's 3 parts to the equation. There's kinetic energy, which is the energy caused by the fluid moving. And very simply, it's 1/2 rho, which is the fluid's density, times v, which is velocity. So you can see if the velocity or the speed of the fluid increases, its kinetic energy increases. Does that make sense?
Uh-huh.
Yep. The second part of the equation is the effect of gravity on the fluid. Now, rho is density, g is gravitational force, and z is the altitude difference. Now, I'm going to just very quickly say that this part of the equation does not apply because this pipe is completely horizontal. If there was some sort of elevation change, like the entryway to the pipe was at 5 feet and the exit of the pipe was at 1 foot, then we would consider this. But this has nothing to do with this example because gravity is not doing any work on the fluid.
Okay.
Okay. And then P, which is the final part, is pressure. So what Bernoulli's equation essentially says is that the kinetic energy of the fluid, which is highly influenced by its speed, plus any work that's done to the fluid by gravity, which in this case is negligible, plus any pressure force. So if you're applying a force to the fluid, all that's going to be constant throughout the entire pipe, no matter which section you're in. This section to the left, the constriction, or the section to the right. It says that this energy equation will stay constant the entire time. And so you can very eloquently say that kinetic energy plus gravity plus pressure here equals kinetic energy plus gravity plus pressure here, and it also equals here. So does that all make sense so far?
Uh-huh.
Okay. This is the final part. So we already said gravity's not doing any work on the fluid, right?
Yes.
The fluid's also not changing. It's air or water, and it's and it's not changing density. So we're going to go ahead and cross out density. The density of the fluid is not changing. So that means that velocity of the fluid and pressure are the only parameters that are actually going to be changing in this equation. So in this section right here to the left, velocity is lower than pressure. If it's going to be equal to this section right here, because we already said that all the sections are equal because of the conservation of energy, if velocity is going to speed up, like we already said it does, pressure only has one direction to go, and that's down. Does that make sense?
Uh-huh.
Okay, well then you get it. That's it.
So say it one more time, just so
Okay.
I'm clear.
So let me. Actually, I'm gonna go here, so I can use my. Hold on a second. Okay, so here there's two sections here. There's section A, and there's section B, and there's section C. And because of what we said earlier, because the fluid is not leaking or changing, and there's no fluid loss, all of these sections must have a constant Bernoullis equation, meaning all of the kinetic energy, all of the gravity work, which is negligible, and any work done by pressure is all going to be the same. So this equation for section A is going to equal the equation for section B, and it's going to equal the equation for section C, which is what I've got down here. I've crossed out the work done by gravity because, like we said, gravity, this is a straight, flat pipe. Gravity's not doing anything. I'm crossing out fluid density because the fluid is not changing. It's the same fluid the whole way through, so I'm crossing out density. The only parameters left are velocity and pressure in each section. Does that make sense so far?
Yes.
Okay. So if the velocity plus the pressure in section A is going to equal the velocity plus the pressure in section B, so VA plus pressure A is going to equal VB. Ooh, B is hard to write with your mouse. Plus pressure B and because what we said earlier, what makes intuitive sense is as the fluid goes into that constricted area, the velocity is going to go up, right?
Mm-hmm.
So VB is higher than VA. If these are going to be equal, that means that only one thing can happen. The pressure has to go down, and this pressure has to be higher for these to stay equal.
Got it.
Make sense?
Yes.
Okay, awesome. So, and then of course on the other side is the same thing. You know, VC and PC have to be equal to VB PB, but because VC is slowing down, to make the equation equal, the pressure in area C has to go up.
Okay.
Okay. So that is Bernoulli's equation, and it's going to help us understand why an airfoil works. After I show you that, you're going to be like, well, why didn't you just explain to me why the wing works? But this is important to understand the pressures and the velocities.
Will this be on the test?
No, it will not.
Okay.
It will not be on the test. But it's good to know, because you just never know what somebody's going to ask you and say, hey, can you explain to me how an airplane wing works? And if you're a pilot, you want to know that answer.
Yeah. Okay.
Yeah. So really quickly, before I talk about the how that relates to how the wing works, I'll just talk about planforms really quick. This also does not really show up in your test, except for the fact that you will be asked what the most popular wing planform is, and it's a rectangular wing. Most general aviation aircraft have rectangular wings, for the reason that when they stall, when you try to climb too quickly and exceed the operating limits of the wing, the rectangular wing stalls at the wing root, so the portion of the wing that is closest to the aircraft right here. And that's desirable because all of your flight controls are on the outside of the wing, out here. And so if the wing stalls at the wing root, you still have control. You still have air flowing over these flight controls out here on the outside of the wing.
Okay.
Yep. We'll talk about stalls in a few slides. But man, where did my? I must have. Let me put a slide in here. I want to draw for you how Bernoulli's equation relates to the how the wing produces lift. So bear with me, because I'm going to draw on the screen here. So here is the wing. Okay, and we already mentioned that your camber line kind of follows equidistant points between top and bottom here. Your mean camber line. Well, the wing sees the what's called the relative wind, or the oncoming air, and it naturally splits into two directions: upper surface and lower surface. And the air travels around these surfaces, and they meet back here at the trailing edge. Okay, so I've got my air molecule right here at the front of the top of the wing, and I've got my air molecule right here. And I'm just, for simplicity, we'll talk in terms of molecules. So we've already seen that the wing's cross section has a curved upper section and a flatter, maybe not completely flat, but a flatter lower section. And your camber line is, equidistant between upper and lower surface. So if this molecule on the bottom of the wing and this molecule on the top of the wing are going to meet each other at the back of the wing, what must that top molecule traveling through the air, does it have to travel faster or slower than the bottom molecule?
Faster?
Yes, faster. So V top is going to be greater than V bottom. Okay?
Because there's a larger distance for it to go?
There you go. That's right. That's exactly spot on. Yeah, because what? Speed equals distance divided by time, right?
Mm-hmm.
Yep. So the higher the distance, the higher the speed. Whew. Higher the speed. Yep. So what did we just learn about fluid dynamics, Bernoulli's equation? The faster the speed,
The lower the pressure.
That's exactly right. So here's my wing right here. All right. So I've got faster speed up here, slower speed down here. That means I've got an area of low pressure up here, and I've got an area of relatively higher pressure down here. And what does that do? It creates force in this direction, because air always wants to move from areas of high pressure to low pressure very naturally. And it creates a suction or a vacuum up here. And that's what causes the wing to produce lift.
Oh, cool.
That's it. Yep.
That makes sense.
Mm-hmm.
Yeah, and And there's you'll find if you Google it and stuff, there's plenty of debates about, whether, hey, the high pressure causes more lift than the low pressure. Or some people think the vacuum creates more lift than the high pressure. I wouldn't look into it that much. Just know for your training that you've got high pressure and low pressure caused by velocity differences to the point that you made, right? And it all goes back to fluid dynamics and Bernoulli's equation. All right. So let's touch base on the lift equation. You will not need to demonstrate all of this math in front of any FAA examiners or during your flight test. You will want to understand some of the concepts behind it. So we're gonna look at the math. I'm gonna highlight the concepts so that when you look at your written test material, you can very easily pick out the concepts and relate them back to the theory, if you will. So the equation for lift is there on the screen, and so are the parameters. And I wouldn't spend time memorizing it, but it is important to understand and take note that in the numerator, you've got air density, rho, and you've got velocity, airfoil velocity. And so that's important because as we've already talked about in some of the other sessions, lift and density are directly related, meaning the denser the air, the more lift the wing will generate for a given speed. If the air is not dense, if it's thin, the airfoil will not generate as much lift. So if you're flying in the mountains where the air is not as dense, your airfoil will not generate as much lift. Airspeed is in the numerator, and it's related by the square. So the faster, if you fly twice as fast, your airfoil will generate four times as much lift. So speed has a significant effect. It's got the most significant effect on the wing's ability to generate lift. And that makes sense because, it's the one thing the airplane does to actually fly. It moves forward. And the third important relationship to know when it comes to lift and the airfoil is that there is a corresponding airspeed for every angle of attack to maintain equilibrium in flight. So what I mean by this is if you're flying straight and level at an airspeed of 100 miles per hour, the angle of attack will be, say, we'll call it 3 degrees, positive 3 degrees. And that will maintain the aircraft in an equilibrium. It won't climb, it won't descend. If you increase the angle of attack to 6 degrees, the aircraft is going to climb and the airspeed is going to go down. And once the aircraft reaches a state of equilibrium, meaning it's climbing at a rate that is constant, you'll hit an airspeed that's constant and the angle of attack won't change. So you could literally go out in your airplane and for every angle of attack, have an airspeed related to that angle of attack. And it varies inversely. So the higher your angle of attack, the lower your airspeed, which is intuitive, right? Because your angle of attack increases, your aircraft climbs, gravity works against your aircraft, and your aircraft slows down. And angle of attack from a definition perspective is the angle between your chord line and the direction of the wind hitting your wing. You're going to see that term quite a bit, relative wind. That is the impact direction of the air hitting the airfoil, which, depending on certain flight configurations, may not be the direction the aircraft is traveling, which can be a little confusing. And I'm gonna talk about a couple of those examples in a few slides. But from a general perspective, in general, it's the direction your aircraft is flying. All right. Does all this make sense to you?
Yes.
Okay. Okay, and there's just a visual on what I talked about before. You've got high speed, low angle of attack, medium speed, and then low speed, highest angle of attack or higher angle of attack. Okay, so that's lift, and the other, I'll say, complex force for discussion is drag. Drag is similar to kind of what you're familiar with when you drive your car. The classic definition of drag is anything in the relative wind that opposes the aircraft's forward travel. So, the landing gear produce drag, the wings produce drag, the entire aircraft produces drag. You stick your hand out the window, that produces drag. Mm-hmm. And so that is one form of drag, and it's known as parasitic drag. It's the any external part of the aircraft that is prohibiting it from moving forward smoothly. So this is the classic drag definition that most people are familiar with. There is a second form of drag, which is I'll say highly complex and requires kind of a thorough understanding of physics, but it's called induced drag. And it is the result of the wings generating lift. Induced drag is, and one of the other kind of, I'll say, confusing points is, unlike parasitic drag, induced drag does not increase with airspeed. In fact, it decreases with airspeed. Take the example of sticking your hand out of your car window. If you do it at 10 miles per hour, you feel, a light breeze on your hand. If you do it on the freeway when you're doing 70, the force of the air almost, pulls your hand back, and it requires a lot of energy to keep your hand in one place, right?
Uh-huh.
Induced drag is the opposite. It's extremely high near the stall speed of the aircraft. So for most aircraft that we fly, 60 knots or so. But it diminishes as the aircraft speeds up. So the important points to understand here are two kinds of drag: parasitic, induced. Parasitic is due to protrusions from the aircraft, landing gear, sticking your hand out the window, different parts of the airplane. Induced drag is the drag that's caused by the production of lift from the airfoils. And these two are inversely related to speed. Parasitic drag increases as you speed up. Induced drag decreases as you speed up. And so the relationship to speed is on this graph here in the lower left. You see parasitic drag increasing, induced drag decreasing. And the total drag curve, which is the sum of these two lines, of the parasitic and the induced, is drawn here as well. And this is an important concept to pay attention to, because you'll note that there is a point where the two lines cross, where the total drag curve is at its minimum. So this particular spot right here is an important point to keep in mind when you're operating your aircraft. That speed is of importance, because that is the speed for which the aircraft is producing the least amount of drag that it physically can produce. Does that make sense?
Yeah, but I don't see how you're getting the sum. The total drag is the sum of the parasite and induced drag. How is that calculated on this graph? Sorry, I'm just trying to understand the graph.
Yeah, it simply is the summation of the two. And I don't know, to be honest with you, I don't know if the scale is correct or not, but it's the summation of the two lines. Yeah, it should. I mean, ideally, it should be where they cross right here is the minimum. Yeah. So the minimum drag line or the minimum drag point speed is of interest because when we talk about your aircraft's ability to glide without power, say you have like an engine emergency, that'll be the speed that you try to maintain because it produces the least amount of drag on the airframe.
Okay.
Okay. Okay. And then I drew that out there. Another chart to become somewhat familiar with, and you'll see a couple of questions on the written test related to this chart, is the coefficient of drag versus critical angle of attack. Now, there is, and I'll see if I have it in here, but the relationship that you're going to use on this chart is the green line, and that's what is of interest when you go for your written test and you take your flight test. The examiner is going to want to know that you understand the relationship between lift and drag and critical and angle of attack, right? When you are in straight and level flight, call it 2 degrees angle of attack, your aircraft is producing a certain amount of lift, your wings are producing a certain amount of lift, and your aircraft is producing a certain amount of drag. And dividing the lift by the drag, you can plot out this line here through the different angles of attack as you approach what's called the critical angle of attack, which for this particular aircraft is 19 degrees. And so the reason the relationship between lift and drag is important is, again, think about it, lift being in the numerator and drag being in the denominator. The higher your lift and the lower your drag, you can reach a certain maximum. And on this particular airplane, that relationship reaches a maximum at about 6 degrees angle of attack. Now you'll notice there's other lines on this chart too. So for instance, CL, I'm going to go back to the lift equation here. So CL is is what's known as a lift coefficient, and it's a value that's tested through flight testing. You can either get it in the pilot's operating handbook for the aircraft, or sometimes you can Google it, like Cessna 172 lift coefficient.
So that's specific to each airfare or each airplane that you're flying.
Yes, this particular chart is specific to the aircraft you're flying.
Okay.
It will change on each aircraft you fly. Yes. And the reason for that is the wings are designed differently. You'll have a different angle of attack for all these different relationships. The one that you're going to want to get to know pretty well on this chart is the lift versus drag, the green line. So the higher your lift in the numerator, and if you can maximize your lift and minimize your drag, you're going to end up at this very top point. That's the point at which your lift is maximum and your drag is minimum. And I've got down here a note that it's your best glide configuration. So that point, 6 degrees angle of attack on this particular airplane, is the same as this point for that particular airplane only. So you can by looking at these two charts, you can draw a relationship between speed and angle of attack.
And is this at any given time, or is this just on when you're lifting off, or is this cruise, or is this ascent, descent, or all of the above?
So I'll take us through a quick flight scenario. So we're sitting on the ground at the airport, and I'm just going to draw a line so I have something to move around the screen here. So we're sitting on the ground at the airport, and most airfoils don't have a 0 angle of attack. I mean, even when you're sitting on the ground doing nothing, it's usually at least like 1 degree. Okay.
Okay.
So here we are sitting on the ground at the airport. Now, let me, if you don't mind, let me just, for the purpose of this, I'm just gonna make a new slide because this will be a lot easier to show. I want to show both charts because I think it's important. Here's our one chart. Here's our second chart. Okay. All right, so we are sitting at the ground. So speed is 0, angle of attack 1 degree. All right, we get onto the runway and we start our takeoff. So my speed is all of a sudden approaching stall speed, which is, close to our takeoff speed. And I'm still at 1 degree angle of attack because I haven't lifted off the runway yet. Now, as soon as I pull back on the stick and take off, my angle of attack is going to increase. And it may, just for sake of argument, let's say it goes up to 4 degrees. So here I am taking off. My speed is now above stall speed. My wings are generating lift. And at some point, I'm going to want to really climb the aircraft. So let's say I'm going to go from 500 feet. I just took off. And I'm going to pull back on the yoke so that my angle of attack is now 10 degrees. That's a very aggressive takeoff angle of attack. And, my speed, we'll just say for now, my speed stays constant right there. And I get up to 5,000 feet and I level off. So now my angle of attack is going to decrease because I'm no longer climbing, and it's going to come down probably somewhere into the 4 to 5 range. And my speed, as I start to cruise, because I'm no longer climbing, is going to increase. It's going to head up this way. And I'm going to start producing more parasite drag than I am induced drag. Now, the point I was trying to make earlier, as far as the importance of some of these relationships and points on the curve, if you have an engine failure, and say you have to glide the airplane back to the closest airport, you're going to want to find an airspeed and an angle of attack configuration where your lift is at its highest, your drag is at its lowest. Does that point right there make sense?
Because you want to be able to go a far distance and make it to the place that you need to make it. So you want to maximize your lift and minimize the drag so you don't go down before you get there?
That's exactly right. Yeah, you want to ensure your aircraft has can travel the furthest horizontal distance given your current altitude. That's exactly right. So the only way to ensure that you can travel a maximum distance with your engine failed is maximum lift, minimum drag. And those points happen to be right here on the drag curve. That is your point. That's the point where your airframe is producing the least amount of drag. And right here from an angle of attack perspective. Maximum lift, minimum drag would be the maximum point on this curve. And minimum drag on this curve would give you this speed.
when you're in flight, don't you always want it that way? Because it would just seem like it'd be more efficient and fuel efficient, and I mean, until you're trying to actually land the plane, right?
True. The only thing you have to consider is the trade-off for time. If man could invent or design an aircraft, an affordable aircraft, where the lowest point of the drag curve was at its top speed or cruising speed, then and it wouldn't be a problem. But there's no possible way to design such an aircraft.
You're going to have more drag when there's more velocity.
Oh yeah. That's right.
So the faster you're trying to get there, this is more like just cruising, coasting.
This is gliding.
Yeah,
this isn't even
gliding.
going anywhere.
Yeah.
This is praying that you make it alive on the ground.
Yeah, got it. Okay. That makes sense.
So if you're cruising, so if you say, hey, I'd love to save gas, but I really need to get where I want to go, and you're up here from a speed standpoint, your parasite drag's going to exponentially go up. By the way, I didn't show the equation, but the drag equation looks very similar to this.
Okay.
Your drag increases 4 times the speed increase because the speed is squared.
Really? Okay.
Yeah. Mm-hmm. So as you increase your speed, your drag increases, and the denominator of lift over drag will increase, and you'll head this way on the curve. You'll head down towards like 4 degrees, maybe 5 degrees. It's also, when you look at these charts, interesting to note the prior point that was made right here. For every angle of attack, there's a corresponding airspeed. So if you look over here, you can pick an angle of attack based on the lift drag curve wherever you want, and there will be a specific airspeed that is associated over here. In the example we talked about, if you're at your best glide speed trying to get to an airport with a failed engine, it's going to be right here. So, if this is, call it 100 miles an hour, then the corresponding angle of attack is 6 degrees.
So if I need to get my aircraft from point A to point B as quick as possible, how is that going to affect this craft?
As fast as the aircraft will travel?
Yeah.
So your speed is going to be high, which means your drag is going to be exponentially higher than it would be if it were over at the minimum.
Mm-hmm.
And in order, excuse me, oh my God. In order to maintain a high speed, let me go back to this chart here just for a visual. You're going to have a small angle of attack. In this particular example, which is not constant for all aircraft, it happens to be 3 degrees. Do you see that?
Yeah.
So assuming that these are the same aircraft, which I'm not sure they are, we're going to take our angle of attack line to 3 degrees. So you can see the increased drag is having a negative effect on this curve. Why? Because the lift over drag, because the denominator is increasing. So the curve is going to go smaller.
Okay.
Makes sense?
Yes.
Yeah. All good questions. That's good stuff. This one, and like I said, it'd probably be good to read the material and make sure you at least understand the background, but you're not going to be heavily involved in the drag coefficient, which is this orange line, or the lift coefficient, which is this red line. Just know that those lines are specific for the aircraft you're studying.
Okay.
Yep. The important points are the minimum part of the drag curve, the maximum part of the lift over drag curve.
And so when you're flying the plane, are you setting the critical angle of attack?
you are setting you're setting the angle of attack indirectly by choosing your airspeed.
Okay. Okay. So you're not sorry, this is a dumb question. But
No.
You're not manually going, okay, I need to get my wing to 10 degrees.
No. But it's funny you asked that because high performance airplanes and expensive, jet airliners have an angle of attack indicator.
Really?
Oh yeah. Mm-hmm. And but the planes we fly don't. The way that you would adjust your angle of attack is by noting the airspeed that you're flying at.
Okay, and the plane automatically shifts the wing based off of the speed that you're pushing the plane to go.
Right. So let's say I'll do two extreme examples. Let's say I pull the plane back to 16 degrees angle of attack, which is, from an angle of attack standpoint, that is extremely aggressive.
Mm-hmm.
What's the airplane going to do?
Slow down.
Exactly. If I hold 16 degrees with constant power, meaning I'm not playing around with the throttle, it will hold that airspeed, whatever that might be. I don't know, 60 miles an hour, 70 miles an hour. If I hold the 16 degrees, it'll hold that airspeed and the airplane will climb. Same in the other direction. If I do, we'll just go over here, a negative angle of attack. Say I push the nose of the airplane towards the earth and I go into a nosedive. What's the airspeed going to do?
Go faster.
Yeah, right. It's going to increase, and it's going to increase to a point where it'll reach a terminal velocity. You'll start going. I'll just make a number up: 180 miles an hour, holding that same negative angle of attack. And so long as you don't add power to help the airplane go faster, it's not going to go any faster.
Okay.
Yep. Now, you reach a point where the plane's not going to fly anymore. So right here, which is in this case 19 degrees. In that example, you've pulled the stick back. You've reached 19 degrees angle of attack. Your airspeed is decreasing. And the laws of physics just don't allow the aircraft to maintain the airspeed. So it decreases beyond stall speed. And the aircraft falls out of the sky, essentially.
Okay.
Yep. Does that all make sense?
Yes.
Okay. These are excellent questions. Any other questions on this?
Not yet.
Yeah, okay. Now this is all good stuff. Okay, so that was lift and drag, the most complex of the four forces. Now you've got thrust and weight. Thrust is, I hate to say it, but somewhat easy, right? It's the force that your engine develops to pull or push the aircraft through the sky. It's either a propeller-driven power plant or it's a jet engine, but it provides a force which, in straight and level flight, opposes drag and propels the aircraft forward. It works directly off of Newton's second law of motion, which was the object's mass times its acceleration is the force. And weight, we spent a lot of time talking about last week. It is one of the four forces. It always acts directly towards Earth. So if your plane is, all the diagrams we look at, makes it look like it acts down through the bottom of the airplane. But if your airplane's flying upside down, then it's going to act up through the ceiling through the roof of the plane. So it always acts in the direction of Earth.
Because of gravity.
You got it. Because of gravity. It's the one force that the pilot has extremely little control over.
Yep.
Everything. Yeah, can't negotiate gravity. You can always adjust the power on your engine to adjust thrust. You can adjust lift by adjusting your angle of attack. You can adjust drag by adjusting the speed at which you fly at, but you cannot adjust gravity. It's always going to be there to bring you back to Earth. Okay. When we talk about flight maneuvers, first of all, that was the 4 forces of flight. Is everything pretty straightforward? Do you want me to hash anything through again?
No, that was really helpful.
Okay. All right. Yeah, like I said, lift and drag are the complex items. Weight and thrust, not so much, but you know, a lot of those high level concepts as far as how angle of attack is associated with airspeed, and the different points on the drag curve and the lift versus drag curve. Those are some of the high level concepts that, as long as you have those down, you'll be in pretty good shape.
Okay.
All right, we're gonna go into some basic maneuvering, and for that, I just want to do a quick overview on aircraft axes. Of course, the basic components of the aircraft are the ailerons, which are on the wings. Let me get my pen out here. So the ailerons, which are on the wings right here. The rudder, which is on the vertical stabilizer, which is part of the empennage right here. The elevator, which is back here on the horizontal stabilizer. And the flaps right here, flaps here, flaps here. And these very fundamental flight control surfaces will control the aircraft about these axes. The ailerons will roll the aircraft about the longitudinal axis. So if you put a line straight through the nose of the aircraft and out the back and fix the aircraft on that line, the aircraft will roll about that line. And the ailerons right here will control the roll of the aircraft along that axis. The pilot does that in the cockpit with the yoke. If this is the yoke right here, as you turn the yoke to the left, the aircraft is going to want to turn to the left. If you turn the yoke to the right, the aircraft is going to want to roll to the right. And it does it by use of the flight control surfaces known as ailerons. As air is passing over the wing, depending on which direction you have the yoke turned, the aileron will either be sticking up into the wind or sticking down into the wind. Tough to draw, but I'll have this aileron kind of downward deflected. Okay.
If one side is going up, the other one side is going down, right?
You bet. That's exactly right.
And is the aircraft built to where I've turned right, and so one aileron is going up and one aileron is going down?
Yes, exactly. For the simple reason that it's just deflecting air.
Okay.
Yep. If this aileron over here is up, it's going to deflect the air and push this wing down. And likewise over here, if this one's up, the right aileron must be down because they move, to your point, they move in opposite directions, and it's going to deflect the air down and push the wing up.
Okay.
Yep. So that's the longitudinal axis. The ailerons, they control the aircraft along its longitudinal axis. We call that rolling. Now take that same line and stab the aircraft through the wings. So in one wing and out the other, and you've got the lateral axis. And when you move the aircraft about the lateral axis, you've got pitching, which is the which is the nose up, nose down, climb, descend, basic maneuvering for the aircraft. The the flight surfaces that control the pitching are the elevators back here. And they work under the same principle that the ailerons work under. They deflect air. So if we go back to our yoke here, the pilot will pull back on the yoke towards them, and that will deflect the elevators up. Which in turn will push the tail of the aircraft down and the nose of the aircraft up. And it's the opposite for the other direction. Push the stick in, elevator goes down, pushes the tail of the aircraft up, and pushes the nose down. So those surfaces work from a deflecting air standpoint, work extremely similar to the ailerons. Does that make sense to you?
Yes. So if you want the aircraft to go up, you're pulling it towards yourself. If you want it to go down, you're pushing it away from you.
You got it. Yep. Yep. And if you want to do a descending left-hand turn, you're going to push the yoke away from you and turn left.
Okay.
Yep. The third axis for the aircraft is going to be straight down through the middle. So enter through the top and straight to the bottom. And this axis is the vertical axis, and it is the axis by which the aircraft yaws. Yawing is controlled with the rudder. So very similar. I don't know if you are a fan of boating, but very similar to how a boat rudder works. It yaws the aircraft about its vertical axis. Same methodology, by deflecting air. And the rudder is controlled with 2 foot pedals on the floorboard of the aircraft. If you want to yaw to the left, you'll push the left rudder in, and yaw to the right, you'll push the right rudder in. Crystal clear.
Yeah, but so this might be a dumb question, but what's the difference between yawing and turning and rolling if you're going right and left? Am I thinking about this wrong?
Yeah, no, it's probably because I made the boat reference.
Okay.
Because in a boat, truly, if you want to turn your boat, you just use the rudder, right?
Yeah.
Yeah. Well, based on the nature of the environment that you fly in, right? You're flying in a 3-dimensional space. You can theoretically turn your aircraft just using rudder. However, you won't be happy with the rate at which you're turning. If you're cruising and you've got to turn 90 degrees in less than 2 miles and you're cruising at like 180 miles per hour, you've got to execute that turn in less than like 20 seconds.
Got it.
So you're not going to be able to yaw the aircraft into that direction quickly and easily. The other thing to keep in mind, and this has to do with aircraft stability, but the rudder in an airplane is a little bit different than in a boat. Of course, I say that I'm not a huge boat guy, so I'm not totally familiar, but the rudder pedals are spring loaded. And so if you hit the rudder pedal, it won't stay there. It will come back. As opposed to the ailerons, if you turn the yoke to the left, it'll stay there. And essentially you could roll the aircraft with just making one control input and the aircraft will continue to roll and continue to roll until you take it out of that roll. The rudder, that's not the case. You will make a control input, like a left rudder, and the airplane's nose will yaw to the left. And as soon as you release that rudder pedal, it's going to go straight back. So it's not a very, I'll say, effective method of turning the aircraft.
Okay, that helps.
Yep. So the vertical axis and the rudder are used to make what we call coordinated turns. And I'm going to talk about that, I think, right now. Before I do that, do you have any other questions on aircraft axes?
No.
Okay. Oh, let me skip to all right, let me talk climbs and descents really quick, but I'm going to further answer your question about coordinated turns in a minute here, okay?
Is there any chance that we could have a three-minute break?
Yeah, go.
All right, perfect. Thank you.
Yep, see you in a minute.
All right, I'm back.
All right, right on. I'm going to, since you asked about the rudder and its use with the ailerons and rolling the aircraft, I'm going to talk about turns real quick because I think it'll help explain that a little bit better too, okay?
Okay.
So turns, when we looked at the four forces of flight and we talked about certain force components. Obviously in straight and level flight, you've got lift, weight, thrust, and drag all acting in their respective directions. Turns, very similar physical concepts when we talk about force components. And the FAA likes to describe it in three different scenarios: your level flight scenario, your medium turn, and your steep turn. And it's important to know the components of all these forces in each of these scenarios. So in straight and level flight, you've got simply weight and lift acting as it concerns turns, weight and lift acting on the aircraft. You have thrust and drag acting as well, but when we talk about turns, we're only concerned about weight and lift. As you enter a turn, the lift and the weight forces break out into components of their forces, individual components, and each one has two components. And as you get to a steep bank turn, each of these components is, I'll say, very pronounced, right? Very definable. And I'm going to go through them here real quick. So steep bank turn, you still have lift and weight. If you remember, weight always acts down towards Earth. The components of weight are what's called centrifugal force and resultant load. So if you take the sum of, and you can kind of see it in the diagram, but if you were to actually do the math behind this, the weight and the centrifugal force, those components add up to what's called a resultant load. Now, let me ask you this. When you're driving on the highway and you take an exit at high speed, and that exit is like a tight turn, you know, like you take the exit and it's going to turn 180 degrees towards like, you know, the toll booth or something like that. When you take that tight turn, what happens to you in your seat?
Well, you shift. I don't know.
Yeah,
I'm trying to figure out.
exactly. No,
Yeah.
that's exactly right. Say I'm taking the exit and I take a tight turn to the right. My body wants to go to the left.
Yeah.
Right? Okay. So that is that's what's known as centrifugal force.
Okay.
The desire for the object in motion to continue in the direction that it was going, even though it's trying to go in a different direction. That's centrifugal force. So that's acting on the aircraft in a turn, obviously. So this airplane, if you're the pilot, you're turning right, and the centrifugal force is shooting out to the left. Now, what you can't feel in your car, because your car's not banking when you're taking your turn off the exit, is the resultant load force. But in an aircraft, because it's banking, there is a resultant load force acting totally parallel to lift. It's acting straight through the bottom of the aircraft. And then you've got weight, which is always acting down towards Earth. On the lift side of the equation, you've got total lift. The wings are still generating lift perpendicular to the wing surface. And that lift can be broken out into a horizontal component and a vertical component. Vertical component acts straight up, opposite direction of weight. Horizontal component acts straight to the right in this example, opposite the centrifugal force. Okay, are you with me so far? Chris, can you hear me? Hey, I think I lost you. Are you still there?
I'm here. Yep.
Oh, okay. Okay. So do you understand that thus far?
Yes. Question is, why isn't so total lift will always be in parallel with the latitude, right? Or perpendicular, I suppose.
Perpendicular with the wings.
Yeah.
Mm-hmm.
Why isn't it like where it's with vertical component? Why isn't it always up?
Because your wings, if you look at the airfoil, and I'll do my cross section here.
Oh, it's the lift is being generated from the wings, and
Yes.
so it's got to be the direction of where they are.
Exactly. Yeah, your lift is always going to act directly perpendicular to your wing surface. Yep.
Thank you.
Mm-hmm. And that lift can be broken out into a horizontal component of lift and a vertical component. Does that make sense?
Yes.
Okay. When it comes to the physics of a turn, the horizontal component right here is what actually turns the aircraft. That is what is responsible for turning the aircraft around a point. So if I'm flying an airplane and I'm flying around a point in space, it's the horizontal component of lift right here that is turning the aircraft about that point in space. Now, I want to come back to rate and radius, but I want to talk about the question you asked a second ago. The rudder, and why what is the use of the rudder, and why isn't it used to actually turn the aircraft by itself? Well, what the rudder does, and really its sole purpose for being in the aircraft, is to coordinate your turn.
Okay.
If you were to rely solely on the ailerons to roll the aircraft and turn about a point, you would find, just because of the way the aircraft's designed, if this is, let's say this is my desired course around this point, you would find that the airplane would turn. You would turn the yoke to the left and roll the aircraft to the left, but it really wouldn't do a good job of holding that turn. It would probably fly somewhere out here. It wouldn't, and the physical reason for that is because the horizontal component of lift is not able to completely overcome the centrifugal force. The centrifugal force is still there, wanting to pull the aircraft out of the turn. Make sense?
Yes.
So that's where the rudder pedals come into play. In order to keep that track, you would have to apply left rudder pedal. In this particular instance, a left-hand turn. In order to keep what we call the turn coordinated. And on your instrument panel, when you look at your turn coordinator, which we talked about a couple of sessions ago, you can tell how coordinated your turn is by looking at this instrument. And this concept really is good for you to understand when you get into your flight training. So I don't expect you to completely understand it now. But essentially, the little airplane here, it rotates and it indicates the aircraft roll. So in other words, as you roll the airplane with the ailerons, it indicates which direction the aircraft is rolling. And this little ball in here indicates whether your turn is coordinated or not. If the ball is out here, then it means that you are slipping past the turn. You're taking this track right here. And you need to use left rudder pedal to get the ball back into the center.
It's kind of like your aircraft's level.
Oh, that's exactly right. That's all it is. It's a fluid-filled case with a little gravity ball in it. And based on whether your aircraft, and in these two diagrams I have, if your aircraft is slipping, like it wants to continue flying away from the point you've chosen, then it's going to be out here. And you're going to have to correct that by swinging the nose to the left with your rudder pedal. And same deal if you're in a skidding turn, it's just the opposite. Let's use the left turn as an example because we've been using it. But if you're in a left-hand turn and you are pulling the aircraft in this direction, and the horizontal component of lift is greater than the centrifugal force, you're skidding the airplane. The aircraft is actually trying to skid around the turn. You will do the opposite. You'll utilize right rudder to point the nose back in the direction of a coordinated turn. The skidding is
you're just going to use whatever rudders in the opposite to overcorrect or recorrect, right?
Yeah, you always want to use the rudder pedal to point the nose in the direction that you want the aircraft to go.
Okay.
Yep. Which is the same as the turn coordinator. If the turn coordinator, if the ball's over here, you want to you want to step on the right rudder to get it to come back. And if it's over here, you want to step on the left rudder to get it to come back.
Okay.
I'll be honest with you, the skidding turn is a lot easier to visualize because, you know, it's kind of like a race car going around a turn too fast, right? Its back end will slip out and it'll skid around the turn.
Yeah.
The slip is a little bit harder to understand because I can't think of a good analogy with a race car or anything like that. It simply is the fact that your airplane is, you're wanting it to make a tight turn and it's not making a tight turn. It's slipping away from the point. Does that all make sense?
Yeah, it does. You know, when you hit pockets of weird weather or just, you know, turbulent air, will this affect these kinds of turns, or is this just based off of how you're flying the airplane using the rudder and the yaw?
So yeah, definitely the types of maneuvering that you do between the ailerons and the rudder will absolutely be impacted by what kind of flight conditions you have. You'll learn if you decide after you get your license, if you decide to get your instrument rating, you'll learn that when you fly in instrument conditions, you only limit your turns to 10-degree turns, called standard rate turns, and you have to keep them coordinated. Otherwise, you'll fall off you'll essentially come off your intended flight path. You know, the other reason that this is taught, and the other reason that coordinated turns are extremely important, is in slow flight operations. If you get to a point where your airspeed is nearing stall speed, which is the point at which your wings stop producing lift, it's the point at which, if you remember, it's the point at which your angle of attack has reached what's called the maximum or critical angle of attack. If your aircraft is not coordinated, let's say, just as an example, let's say this particular picture right here, your airplane is turning final approach to land at a runway. If you're coming around this left-hand turn and it's not coordinated, you stall the airplane, there's a chance that the stall is not going to be recoverable. You will not actually be able to get the plane back into a flyable orientation. That's what they call a spin.
Okay.
So coordinated turns happen to be an extremely important aspect of your flight training.
Okay.
Yep. All right. So that was coordinated turns. Just one more time, in case I didn't make it clear enough. You know, how coordinated your turns are a direct impact on, or are directly impacted by your horizontal component of lift versus your centrifugal force. So it's just important to know that the skidding versus slipping are highly impacted by those two force vectors. You also want to become familiar with turn rate and radius. Radius is probably an easy one to understand. It's simply, you know, if you've got a large radius turn, it's not, you know, it's not as tight as a small radius turn. To execute a small radius turn, you would have to have a higher bank angle to complete the turn quicker. And then that goes into the discussion on rate. Rate is how quickly you are turning, and it's expressed in degrees per usually minute, but I've seen it expressed as degrees per second. So if you are in a and by the way, degrees is degrees on the compass. So it's not the bank angle, it's degrees on the compass. So if this is north, so 360, This is south 180. And by the way, do those numbers make sense to you, right?
Yes.
Yeah. Okay.
So we're on 90.
90 and 270. So if you're traveling north and you execute a left-hand turn and start traveling south, if you complete that turn in 1 minute, then your rate was 100 degrees per minute. Very, very simply put. And like I said before, if this is your intended turning circle, this is your intended track, that would be a smaller radius than this intended track out here. And then we just talked about slipping and skidding. So all those terms, all that fundamental stuff, does that make sense to you?
Yes.
Okay, cool. All right, I skipped over this one. I want to touch on climbs and descents. We're actually, this is pretty timely because Thursday we're going to talk a lot about climbs and descents during the session on performance planning. But for now, it's important to kind of understand the relationship between the four forces and their relative components, between those and the aircraft when it climbs and when it descends. We already kind of touched on some topics like an increased angle of attack will cause the airplane to climb and cause the airspeed to decrease. And, on the other end, if you nosedive the aircraft in a negative angle of attack, your airspeed will increase. So, there's that relationship between airspeed, climbs, and descents. There's also a relationship to power. So if you're cruising along at 100 miles per hour and your aircraft has excess power to climb, you can use that power. You can increase the power on your engine by using the throttle, and naturally the aircraft will want to climb. Now, you can obviously force it to not climb through holding the elevator, right? Holding the yoke and making sure it doesn't climb. But then, the other physical phenomenon will take over and it's just going to want to speed up. So what you'll find, and this will become really obvious when you start your flight training, but when you're flying along in equilibrium, straight and level flight, if you increase the power substantially, the aircraft's naturally going to want to climb. As you decrease the power, the aircraft is going to naturally want to descend. And if you, like I said before, if the pilot physically keeps the aircraft from descending by holding on to the elevator control and keeping the aircraft from pitching down, the airspeed is going to decrease to a point where if you've pulled the power enough, you may stall the airplane. It may not be able to hold the altitude that you want it to hold. It's, keep in mind too that, like we said, in steady state equilibrium flight, thrust and drag act in the same plane, lift and weight act in the same plane, but that's not always the case. You can be climbing, like we said before, and you've got components of weight that are working against thrust. In fact, I put the picture of the space shuttle here because conceptually speaking, a aircraft like a rocket, like the space shuttle, its thrust acts against weight and drag going in the same direction. So, you may not always be presented with the simple equilibrium when it comes to climbs and descents. You may not always be presented with, okay, straight and level flight and pull the stick back to climb a little bit. someday you may find yourself flying a high performance airplane or something where it has enough thrust to overcome, weight and drag going in the same direction.
Okay.
Yeah, and so Thursday we'll talk about how to actually calculate different performance parameters when you're, like, for instance, how to plan a climb. What airspeed do you use? How long will it take you, to climb to a certain altitude given a certain airspeed and density, altitude, and stuff like that. So, all right, turns. Okay, let's do a time check. All right, we're doing pretty good. One thing that I mentioned a couple times when we were talking about lift is stalls. And before you get interested in flying and you start doing some research on your own, most people think that when you say an airplane stalls, they think that the engine quits. But the truth is, when an aircraft stalls, the wings are stop generating sufficient lift to actually overcome the other forces of flight, and the aircraft falls out of the sky, essentially. Scientifically speaking, as the airfoil begins to increase its angle of attack, the laminar flow over the top of the wing, and laminar is just a fancy word for smooth, the smooth flow over the top of the wing starts to break up and starts to become turbulent. The air that travels over the top of the wing wants to stay near the wing surface because it wants to meet the air flowing under the wing at the trailing edge. As you increase angle of attack, it can no longer do that, and little pockets and voids and eddy currents of air start to form on top of the wing. If you increase the angle of attack to what's called the critical angle of attack, the wing will stall. It'll stop producing lift altogether. And if not corrected, the airplane will essentially just become a paperweight. It'll fall right out of the sky. Important to note, and there are physics behind this. No one will require you to understand all the physics behind it. In fact, if someone asked me, I probably wouldn't be able to explain it very well. But it's important to note that the stall characteristics of the aircraft are solely dependent on angle of attack, and you will always stall the aircraft at the same angle of attack, regardless of other parameters, such as weight. A lot of students, myself included, when we first learn about airfoils, think that the heavier the aircraft is, the quicker it will stall from an angle of attack standpoint. But it's not true. The airfoil will actually always reach its critical angle, and then it'll stall. So it's not extremely intuitive. Just know that regardless of whether you've got the flaps deployed, whether the aircraft's fully loaded or empty, etc., it's always going to stall at the same angle of attack. The one parameter that does change is the speed. So your aircraft will stall at a different airspeed depending on how heavy it is, whether you've got flaps deployed, landing gear deployed, where the weight is loaded in the aircraft, stuff like that. So just know the airspeed can change, but the angle of attack will always be the same.
Okay.
Now, to kind of build off of the point that your airspeed can differ, but your angle of attack will always be the same. Load factor, weight, and load factor actually have a pretty significant impact on stall speed. And I've got it depicted here on this slide, but one thing that you'll want to become familiar with, especially after you've got your written test out of the way, you start your flight training, you're going to want to show that you're going to show your instructor that you're aware that when you turn the aircraft, when you roll the aircraft, your stall speed increases exponentially. And this is caused by the increased load factor on the wings that we talked about earlier. If you remember, you've got your weight, which when you're in a turn, you've got your weight, which acts directly down towards Earth. You've got your centrifugal force, which is that force that kind of pushes you to the outside, when you're making a turn. And you've got your load factor, which is this other this other force component of weight. And as you turn your aircraft through 10 degrees of bank, 20 degrees of bank, 30 degrees of bank, you keep increasing bank angle, you're increasing that load factor exponentially. And with an increased load factor, you have an increase in stall speed.
Increased load factor equals increased stall speed?
Correct. Yep. And I'll say the way to understand this from a physical perspective is if your aircraft is flying straight and level, and I'll just make up numbers. Let's say it weighs 1,000 pounds. As you try to climb the airplane, you will pull back on the stick and you'll find an airspeed to climb at, and your aircraft's going to climb with a 1,000-pound aircraft, okay? Let's use that same example where you're going to climb your aircraft in straight and level flight, but let's say you put a 5,000-pound weight in the back seat. You try to climb that aircraft, it's going to be a lot more difficult to climb. Does that make sense?
Yes.
Okay. This is the same thing. When you increase bank angle, like it is in this picture below, you're increasing the load factor of the aircraft. The aircraft still weighs the same, but the load factor is increased. And if you know, let me go back here, go back to this slide to just show a picture. The load factor opposes the lift that the wings generate, right?
Uh-huh.
So in the example where you're flying straight and level and you've got the 5,000-pound weight in the back seat, we both agreed that, hey, if I want to try to climb the airplane's going to have a pretty tough time compared to the 1,000-pound weight. Well, same thing. As you turn the airplane and increase this resultant load, you're essentially doing the same thing in a turn as you are in that straight and level example. You're adding enormous amounts of quote-unquote weight as a force vector, which the wings just aren't able to overcome from a lift perspective.
Okay.
Makes sense?
Yes.
Yep. So if I go down here, by the way, from a physics perspective, each bank angle has a specific load factor associated with it.
Okay.
So I don't have the table up here, but oh yeah, I do. It's right here. So 60 degrees, which is this picture right here. This aircraft is turned at a 60-degree angle. That is a 2G load factor. So essentially, you've got 2 times aircraft's weight, 2 Gs, acting in that direction.
Okay.
And you can feel this, by the way, when you're on the airplane. Obviously, you fly commercially like all the time, right?
Yep.
Have you ever been in an airplane where a pilot makes, maybe not an aggressive turn, but makes a pretty decent bank angle turn?
Yeah, to get to an airport.
Yeah, you feel your when they do that, you feel yourself like get pressed into the seat?
Yes.
That's the load. That is the load factor.
That's the load factor.
Mm-hmm. Yep. So, you know, for instance, if that pilot does a 60-degree turn, you find the bank angle on the chart, 60 degrees. You find the associated load factor line. You can see it's 2 G's. And from there, you can find the stall speed increase. In a percent of stall speed. So if your stall speed was originally 100 miles per hour, it is now 140.
Okay.
Yep. So this is significant because typically with small aircraft, your cruise speed could all of a sudden become your stall speed. You could be cruising along at 140 miles per hour, which is not unheard of in a small aircraft, and all of a sudden attempt a 60 degree turn, and all of a sudden you've stalled your airplane. You could essentially your wings could stop producing lift and you could fall out of the sky.
Oof.
Yeah. That's why I've never been in an airliner that's done a 60-degree turn. That's pretty aggressive. Typically, you know, you're down in between 0 and 20 degrees. But so important point here, load factor, which is that pressure you feel in your seat when you turn, is highly influences the stall speed of your aircraft because it acts opposite the direction of lift.
Okay.
Okay. Make sense?
Yes.
All right. Okay. Stability is the next topic. We've got 10 minutes. First of all, what questions do you have? We've covered like a freaking ton of material.
I know. I think I'm just taking it all in, and everything seems pretty clear.
Okay, you're sure about that? I mean, anything's fair game. It really is, especially when it comes to like, you know, angle of attack and drag and stuff like that. If you think of something, don't hesitate to shoot me a note or whatever.
Okay, thanks.
Okay, let's do this. I'm going to cover just a quick topic in stability, and then I'm going to skip to a discussion question. We'll go through the discussion question, then we'll wrap up. Okay.
Okay.
Okay. So stability, not completely related to aerodynamics. However, it is a concept that you'll become familiar with. You certainly want to know it for the written test, and it's just a part of flying the airplane. So you'll be introduced with it from the first time you get in the airplane and fly with your instructor. There's 3 categories of stability: positive, neutral, and negative. And then those are the categories. And then you've got 2, call it overarching types. And those 2 are dynamic and static. We're going to focus mostly on static, although dynamic is covered on the written test. But I am going to explain it. It's not tough to understand. It's basically static plus a couple more things to consider. So first off, we're going to start with static. Positive static stability, and these pictures they're you know, simplistic, kind of dumb, but they really do a nice job explaining. If you take an object like a ball and you push it on this curved ramp in this direction, if it exhibits what's called positive static stability, the ball will initially return back to its normal position. That's known as positive stability. It reacts positively to a force input or a control input. Along the same thought pattern there, neutral would be if you push this ball and it just remains in the same spot that you pushed it to. And then negative would be the complete opposite of positive. If you push the ball and it initially begins to move further away from you, from the initial point from where you pushed it. These examples can be translated into aircraft stability type examples. And let me just go through a couple of them, because like I said, these are kind of simplistic, even though it makes intuitive sense from a visual standpoint. When you're flying the airplane, the different flight controls, I even mentioned one before, the rudder, exhibit more of a positive static stability type behavior. When you push on the left rudder pedal and release it, the aircraft will initially want to return back to its normal position. So the rudder, the rudder exhibits positive static stability. Unlike the ailerons, I had mentioned when you roll the aircraft by turning the yoke to the left, the aircraft rolls about its axis. If you let go of the yoke, it will initially want to stay in that position. So you could say that the aileron control surfaces exhibit or cause the aircraft to exhibit a neutral static position. And it's tough to find an example on an airplane for negative, and that's a good thing. It would be not very desirable for an aircraft to have any control surfaces or control axes where a negative stability situation could happen. I can't think of one, and it really is a good design feature for an aircraft to either exhibit neutral or positive stability type behavior. So does that overall fundamentally make sense?
Yes.
Mm-hmm. Now, you'll see it's not really, honestly, it's not really covered too much, but it is on the written test. You barely ever hear it in application, but dynamic stability is static stability, but with time taken into account. So if you remember when we talked about like the example of the ball, and I said, hey, if you push this ball up the ramp, its initial tendency will be to return back down the ramp to its initial starting spot. Well, the key word there when we're talking static is the word initial. The initial, the ball's initial tendency is to move back to its original spot, or its initial tendency is to stay where it's at if it's neutral, or its initial tendency is to continue moving in the direction it's going. That is all static descriptions. Dynamic is the same, static, but with a time element. For instance, positive dynamic stability would be if you push the ball up the ramp and it initially comes back towards the middle of the ramp, and then because you pushed it too hard, it goes up the other side of the ramp, and then it comes back and it comes back and it eventually makes it back to the center of the ramp. Does that make sense?
Yes.
Yeah. So it's like you push the ball too hard, so it's here. Then it rolls all the way back here, so it's here. Then it rolls here, here, here. Yeah. So you can see here's your time axis this way. So this particular graph, if you will, is exhibiting positive dynamic stability. The opposite of that, as you might be able to guess, is negative. You push the ball and it continues to go out of control further away from the ramp. And neutral dynamic stability doesn't really exist because there's no time. Time doesn't really matter. It moves and it stays. So from an aircraft control, surface control, and maneuvering standpoint, you won't find a lot of aircraft that are designed with negative any stability, dynamic or static, in mind. The only one I can really think of is if you push the nose of the aircraft over, if you push forward on the control yoke to actuate the elevators, therefore pushing the nose down, and maybe your aircraft is nose heavy, maybe your center of gravity is too far forward, it may continue to nose over and enter a nosedive. That right there would probably be the only example I could think of where you might see negative stability in the aircraft. Most aircraft are designed with positive and neutral.
Okay.
All right. That's stability. It's very simply put. That's what you'll need to know from a stability perspective.
Okay.
And that's pretty much a wrap on the material, unless you've got any, questions, things that just didn't make sense, any of this stuff.
No, I'm sure I'll think of some later on and I can email you.
All right. What about anything on the other material that you can think of, stuff not related to this that you want to, that you think about and that you want to ask in person?
At this point, no.
Okay. All right. Well, Thursday we're doing another session. I've already got the quiz and the answers for this particular session up in the shared drive. If you want to take a look at that, go ahead.
Cool.
Yeah, and yeah, like you said, if something comes up just not making sense, shoot me a note or email or Slack or whatever you want to do.
Perfect.
All right. Sounds good, Chris.
All right. Thank you so much for accommodating me and redoing this.
No issue at all. Love to do it. We'll talk Thursday.
All right. Thanks, Adam.
See ya.
Bye.